Welcome to Spring LIB.
Okay, in this problem, we're asked to do a little bit of a smoke detector design, which is going to involve the photoelectric effect. We're given this table of different elements and their associated work functions. Recall that the work function in electron volts is the minimum amount of energy needed to dislodge an electron and eject it from the material, these photoelectrons, using light. So this is the minimum amount of energy an individual photon would need to eject an electron. So we're asked for quite a number of things in this problem. There are numerous parts. To start off, we're given a lambda of 270 nanometers, and we were asked what materials will make photoelectrons for this particular lambda. We're then asked for which material will give us the largest kinetic energy of ejected electrons and what the associated velocity of these electrons would be. Then we're asked to look at some specifics for gold and sodium. We're asked for the maximum lambda to make photoelectrons for gold, and we're asked for the maximum kinetic energy for sodium using the lambda from part C. So the equations we'll need for this problem is the photoelectric effect equation, that the kinetic energy of electrons is equal to the energy of the light shined on the material minus the work function. We need to know the energy of light is proportional to its frequency by the Planck constant and inversely proportional to its wavelength. And of course, we need to know the kinetic energy of electrons, or kinetic energy of any object with mass, which is 1/2 mv squared. Okay, so let's jump into it. Okay, so starting up with part A, we have our table of values. So the first thing we can do is we simply need to find the energy of per photon of this particular light with our particular wavelength. So we can use E equals hc over lambda. We will use the electron volt version of the Planck constant, so you can get a result in electron volts. And then we can compare that to the table and see which materials have a work function less than this value we're computing. So it's 270 e to the negative 9 meters. Doing this computation, we have a result of 4.59 electron volts. And there will be 3 on our chart that will work, that has a work function less than this. Aluminum. So aluminum has a work function of 4.3, so it qualifies. Silver also has a work function of 4.3, so it qualifies. And lastly, sodium. This is elemental sodium. Has a work function of 2.7, so it qualifies. So of the list, these are the 3 materials that have work functions less than the energy per photon of our light. So these are the ones that will produce photoelectrons. And of these, sodium has the smallest work function, meaning, using the photoelectric equation, since K is equal to E minus phi, and E is what we computed, and it's not going to change in this section, we need to minimize phi to get the largest K. Sodium has the smallest phi available, smallest work function, so that will result in the largest kinetic energy of photoelectrons. So we can actually solve for what that kinetic energy would be. It'd be 4.59 eV minus 2.7 eV, which results in 1.89 eV. This is the maximum kinetic energy of photoelectrons we can get from the various materials at this particular lambda. And using kinetic energy equation and solving for V, we would end up with 2K over M, root 2K over M. Plug in values, our value for K, and the mass of an electron, 9.1 e to the negative 31 kilograms. We would get a velocity of 8.15 times 10 to the 5 meters per second. Great. So now let's move to another page and look at some specifics for gold. we were asked for the longest lambda of light that we could shine on gold in order to produce photoelectrons. So starting with the photoelectric equation, K equals E minus phi. So at the very, very minimum, at this threshold, we would produce photoelectrons with a kinetic energy of 0, which would otherwise, all of the energy goes into just dislodging the electron, and there's none left over for actually giving it some real speed. Thus, K would be 0 at this threshold. So E would be equal to the work function. And we can figure out what wavelength of light is that threshold lambda. So E is equal to hc over lambda, which is equal to the work function. Solving for lambda, we get hc over the work function. And plugging in values, we would get 2.43 e to the negative 7 meters, or about a quarter of a micrometer minimum wavelength. Now, last thing we were asked to do is look at sodium, what the kinetic energy of photoelectrons for sodium would be if we shined light with this wavelength, the 0.24 micrometers, what we found for gold. What would the kinetic energy for sodium be? Use K equals E minus phi. Which is equal to hc over lambda, of course, minus phi. And this hc over lambda would simply be the 5.1 EV for gold. Subtract the 2.7 for sodium, electron volts. And that difference would be the kinetic energy of photoelectrons for sodium if we shine the light associated with gold. So these are all of the results that we need for this particular problem. We repeatedly use the simple photoelectric effect conservation of energy equation, K equals E minus phi. And we looked at it from pretty much every angle you possibly can. So that's it. Thank you very much.